this video, we are going to analyze the motion in two dimensions. The motion in two dimensions is richer than the motion in one dimension because the direction can be infinity direction. In one dimension, you can be at the position +5 or -5. Now, if I say that you are from the origin at 5 meters, you can be in any position around. You have infinity points to be at the distance 5 meters plus 5 meters. So you have many possible directions to be at 5 meters. So now it's different. The treatment that we are going to do is different. We need to use vectors to describe the motion. And using vectors and using these quantities is that will allow us to write equations for vector velocity and vector acceleration. So imagine that you have the point P here, and here is O. O is where you live, and P is maybe where is the university where you study. So when you move from O to P, there is a displacement vector, and this is the vector that have magnitude, all this magnitude, the length of the vector, and it has a direction. To specify the direction, you need to put the vector in a system of coordinate and say, okay, this is the positive axis, x, and my direction where I'm going is 30 degrees from the x positive direction. So the arrow indicates how far is O from P. Let's say 10 kilometers. And it indicates in what direction is P, 30 degrees. Okay, from O to P, there is a vector, and this vector is a displacement vector. So you can think of a vector like an operator. It moves you from here to here. So it displaces you. Or you can think this is the position vector. This is the position P at the time t. The object is here respect to the reference point O. He is at 5 kilometers maybe, and at 30 degrees respect to the positive axis. Okay, now once that we understand that there are two types of physical quantities, one doesn't need any direction, like the mass doesn't need any direction, the temperature doesn't need any direction, and they are named as an scalar quantities. The kind of quantity that we are going to deal with are different. They need directions. So they add in a different way. So we need to add quantities that have magnitude and direction. And we need to postulate a way to say what is the law, how we sum two vectors. So the vectors, when we deal with a physical quantity that is a vector, we always write the arrow here. The v is a vector, the velocity is a vector, so we write the arrow. The acceleration is a vector, we write the arrow. The force is a vector, we write the arrow. Not writing the arrow can make you to make many mistakes. You must write the arrow. So, vectors have magnitude and direction. Two pieces of information. You need two pieces of information and different kind of information. One information is about the magnitude, the amount of distance that are involved here, and the other kind of information is about the angle, its direction. Okay, let's go. So let's go to define how to sum a vector, how to sum two vectors. Let's say that your initial position is at P, so you are here. So from my point of view, from my point of reference, I say that you are here. Okay. Now you are here, you take your car and you move from here to here. When you arrive here at the point Q, I will say your position is here. Have you changed your position? Yes. What is the change in position? The change in position is the vector that goes from P to Q, and we call it delta R, the change in the vector R. So we start with this R initial, we make a change in our position, and we obtain a new position. So the equation that we will work is like this. R final is equal R final vector R final equal vector R initial plus the change. So based on this way of defining how to sum vectors, how we have defined how to sum vectors, there is a rule here that is named the rule of a parallelogram. The first vector goes from O to P. The second vector goes from P to Q. And the sum goes from O to Q. So the sum of two vectors is obtained by drawing a vector that goes from the tail of the first one, from the tail of R initial, to the head of R final, of the second one. So the R final goes from the tail of the first to the head of the second one. Perfect. So to sum vectors, we use a rule that is called the parallelogram rule. And the rule, what it says is, you sum like this. So if you want to think as a vector, as an operator, the first operator will make a motion like this. The second operator will do a motion like this. So you start here, and later on, you go here by the operation Ri. Later on, you go here by the operation delta R, the change in the position, and this is equivalent like going from here to here. So the sum R is R initial plus the change in R. You see there is a rule that is the parallelogram rule. You have to follow the arrows. You have to follow the arrow. This one plus this one is this one. So the vector C is the sum and start on the tail of A and end on the head of B. How to sum vectors. For example, if you want to sum these two vectors, this is a way of summing geometrically speaking. We will learn how to deal algebraically with vectors soon. Wait, so if you want to sum this vector with this vector, it will be this vector. Okay, if I want to sum this vector with this vector, it will be this vector. So this is the sum. Okay, this is the sum. If I want to sum this vector with this vector, will be this vector. This is the sum. If I want to sum this vector with this vector, will be 0. Why? Because the first vector make a motion, it translates you from here to here. And the second one, it makes a motion it makes an operation to move you from here to here. So you are at the same place. So nothing has happened. So the sum is 0. So you can play with the sum this by this. The sum of these two vectors is this vector. For example, how is the sum of this one? This plus this plus this plus this. The sum should be 0. The sum of these four vectors is 0 because you start here, you move from here to here, later on you move to here, you move to here, you move to here, and you end it in the same position that you were. So the sum of the four vectors, like this one, should be 0. So you practice the sum. A master in physics, they have a lot of questions about the sum of vectors. Also, my assignments in conceptual question, you will find a lot of questions about the sum of vectors. The basic picture that you need to have in your mind is this is A, this is V, and this is the sum. The sum is A plus V. You can distortion this picture, this figure, and always when you see a problem, you may distortion this figure, but don't change the arrow, the direction of the arrow. The direction of the arrow is like this. Okay, let's go to see. So let's go to analyze what it means to multiply a vector. Let's say that you have a vector, so you have a magnitude and you have a direction. You have this direction, this one, this direction, this direction, this direction, this direction, okay? And you have also this direction. Oh, this is, I'm sorry that I can draw. Okay, the same direction. So you have a vector R. What is the vector 2R? The vector 2R is to put the vector R twice. You put the vector R here, and you put the vector R here, and 2R means sum R with R. 1R with 1R, 2R. So the vector 2R is the vector that have the same direction, but double magnitude. So this is the vector 2R. Now, what it means minus R? So the vector R is the vector that has certain amount of magnitude, let's say 5 meters maybe, in certain direction. The vector minus R is the vector that have the same magnitude but opposite direction. So if this is the vector R, this is minus R. And minus 2R, it will be this plus this minus R. And the sum will be this vector. This is the vector minus 2R. Minus 2R is the vector that have the same magnitude that it has the vector R, but in the opposite direction. Okay. Now let's go to analyze how to subtract vector. We will see subtraction of vectors when we use Newton's law, or even in Newton's law we will see a lot of subtraction of vectors. So imagine that this is R1. This is an unknown vector, and this is R2. The difference, the subtraction of R2 minus R1 is, let's say that I call this the vector X. I don't know who is the vector X. So I would write one equation according to what I have learned, that it will say R1 plus the vector X equal R2. So who is X? The vector X is R2 minus R1. So now I have learned that this is the vector R2. This one is R2 minus R1. Okay. And knowing that this is the vector R2 minus R1, I learned the following thing. The vector R2 minus R1 is the vector that goes from the head of R1 to the head of R2. Is different than with the sum. R2 minus R1 goes from the head of R1 to the head of R2. R2 minus R1 goes from the head of the first to the head of the second. So you have learned how to draw the vector R2 minus R1 given to vector. You can always find R2 minus R1. The other way to say the same thing is to say that R2 minus R1, this vector, is the vector that you have to add to R1 to obtain R2. It's correct. This is the vector that you have to add to R1 to obtain R2, because remember our picture. A, V, and the sum. C. Oh, it's clear this. Another way to see this difference of R2 minus R1 is to write this in the following way. R2 minus R1 is the same that R2 plus minus R1. This and R2 minus R1 is exactly the same. So I will make a sum. So R2 is this one. Minus R2 is this one, is the same vector with the same magnitude as R1, but in different direction. So what will be R2 plus minus R1? What will be this vector R2 plus this vector minus R1? Oh, it will be this one. This one is R2 minus R1. So this vector R2 minus R1, by the way, is the same vector that this one, than this one. This is the vector also R2 minus R1. It's the same vector. Okay. So let's go to practice. What is here R2 minus R1? R2 minus R1 is the vector that goes from the head of R1 to the head of R2. Who is this vector? This one. Okay. In this case, what is R2 minus R1? R2 minus R1 is the vector that goes from the head of R1 to the head of R2. This one. What is here V2 minus V1? V2 minus V1, V2 is here, V1 is here, V2 minus V1 is the vector that goes from the head of V1 to the head of V2. So it will be this vector. This vector is V2 minus V1 and represent the change in the velocity, because V1 plus the change in the velocity is V2. Do you see the picture? V1 plus the change in the velocity is V2. A plus V equals C. A plus V equals C is the same picture. What is here? For example, R1 minus R2. R1 minus R2 is the vector that goes from the head of R1 to the head of R2. So it will be this vector, R2 minus R1. Perfect. What will be R2 minus R1? R2 minus R1 in this case will be, can you tell me? R2 minus R1. So I will take R1, R2 minus R1 will be equal to R2 plus minus R1. So I have R2 here. Now I have to add the vector minus R1. The vector minus R1 is this vector. And what is R2 plus the vector minus R1? Is the vector 0. Is the 0 vector. R2 minus R1 is the 0 vector. You may think like this also if you want to think in this way. R1 is the operator that moved me from here to here. Okay. And R2 is the operator that moved me from here to here. And minus R2 is the operator that makes me a move from here to here. So I have one operator here and another operator going in the other direction, minus R2, so it will be 0. If this is in the same direction, you know delta V will be the change in the velocity. In this case, if it represents velocity, it will go from the head of V1, of V initial, to the head of V final. So the change in the vector will be here. This is the change. This is the change in V. Or in other words, the change in V is the vector that you have to add to V1 to obtain Vf. And you will find a lot of examples in Master Physics and also in my assignments for conceptual questions. So now we are going to define how to define vectors in 2 dimensions, how to define velocity in 2 dimensions. We will define the velocity as the change in position per unit of time. We can know how to divide by an scalar because it's the same that is how to multiply by a vector with an scalar we already studied. So in the same way that the velocity v, and it was defined like delta x divided by delta t, we can define the vector velocity as the change in the vector position per unit of time. And with the acceleration, it happened the same thing. We define the acceleration as the change in velocity per unit of time. It's the same equation that A equals the change in velocity per unit of time. The only difference that now the equation involves vectors. So the change in velocity involves a vector, and this is a vector. It's something different, especially when the 2 vectors v initial and v final, delta v, they are not in the same direction. So if the magnitude of the velocity doesn't change, but the direction of the velocity change, then there is an acceleration. Why? Because let's say that the velocity initial is like this, v initial. And let's say that v final is like this, going up, v final. I put the 2 vectors also with the tail together. So what is the change in the velocity, even if this is 5 meters per second? And this is also 5 meters per second, that there is no change in the magnitude of the velocity. There is a change in the vector velocity, and the change in the vector velocity is this vector, the vector that goes from the vector initial to the vector final. So there is a change in the velocity. So the numerator is not zero, even if the magnitude of the velocity have not changed. The numerator is not zero. And if this situation happens in certain times, you will divide by the delta time, by the interval of time that happened. So the acceleration is in the same direction as the change in the velocity. And the velocity is in the same direction as the change in the position. If the change in position goes to the right, the vector velocity goes to the right. If the change in position goes in this direction, the velocity goes in this direction. So the velocity is parallel to the change in position, and the acceleration is parallel to the change in velocity. Perfect. So consider now an object that is at the position R1 at the time t1, at the position R2 at the time t2, so it has changed his position. R2 minus R1 is the change in the position. So the velocity is the change in the position per unit of time. Imagine that this has happened in 1/2 of a second. 1/2 of a second, so it has happened in 1/2 of a second. The velocity will be v equal delta r, this vector, divided by 1/2, so it's 2 delta r. So the velocity is parallel to the change in the position, and the velocity is here, but indeed I cannot make the picture of the vector here because this is the x and this is the y, and I should do the vector in the plane vx, vy. You will see this, you will see later on this small detail. So, first case for the vector acceleration, to just insist, vector acceleration doesn't mean necessarily that because there is no change in the magnitude of the velocity, there is no acceleration. This is not acceleration. Acceleration means that if there is a change in the vector velocity, then there is an acceleration. So imagine two objects, two cars. One is going at initial velocity, it's the same car. One is going at this velocity. The other one is at a later time is going at this velocity. So the car is the same car. The car has increased its velocity in a certain amount of time. What is the change in the velocity? The change in the velocity is here. This is the change in the velocity. Is a positive change in the velocity? Well, this depends how you define the positive direction. If you define the positive direction to the right, this is a negative change in the velocity because the change in the velocity is to the left. Okay, now, where is the acceleration? The acceleration is parallel to the velocity, so the acceleration is the change in the velocity divided by the time elapsed between the situation when the object was at velocity vy, maybe 100 meters per second, and the situation, the time when the velocity was 200 meters per second. So if this has happened in delta t equal 2 seconds, and the change in the velocity, in the magnitude of the velocity, is, let's say, from 200 meters per second to 100 meters per second, the change in the magnitude of the velocity is 100 meters per second. And the acceleration, the magnitude of the acceleration, will be the change in the magnitude of the change in the velocity divided by the change of time, so it will be 100 divided by 2, it will be 50 meters per second squared. But this is the magnitude of the acceleration. What is the vector acceleration? The vector acceleration will be minus 50 meters per second squared, going in this direction, And we can if we name the positive direction like this, the direction I, so we can say that this is going in the direction minus I. If we say that the positive direction is the I, we can say that the acceleration is minus 50 meters per second squared in the negative direction. Now, look the second case. The second case is when the car is not changing its magnitude of the velocity, but is changing the direction. So initially, the velocity v sub I is like this, and finally the car is moving like this, so the final velocity v sub f is like this. Pay attention that I have put v sub I and v sub f with the head together, with the tail together. So now I can find the delta v. So if the object goes like this, and later on go like this, there is a change in velocity. In this case, there is acceleration also. And the acceleration is going in this direction, in the direction where the change in velocity exists. This is the acceleration. And in this case, the acceleration is not parallel to v sub f, is not parallel to v sub I, is in another different direction. So you have to pay attention that now in 2 dimensions things can change. In 1 dimension the acceleration is parallel to the velocity or anti-parallel to the initial velocity maybe, or whatever, but always is parallel or anti-parallel. Here the acceleration is not parallel to the initial velocity, not parallel to the final velocity. So tension is something different. So to make the summary, case 2 say that the acceleration and the velocity do not need to have the same direction. And meanwhile, in the first case, acceleration is in the same direction that the velocity, and the acceleration is being used to change the magnitude of the velocity, to change the speed, to accelerate the body in the normal, using the vocabulary that we use in our normal day. No? The second case is different. Even if the magnitude of the velocity have not changed, there is a change in the vector velocity, because the vector velocity initially was going in this direction, finally was going in this direction, so there is a change in the vector velocity, v initial, even if the magnitude is 100 meters per second here, and here is also 100 meters per second, even in this situation, there is a change. And the change on velocity is from the initial to the final. This is the change in velocity. And in this case, there is acceleration. So always that an object changes his velocity, there is an acceleration. And he can change his velocity, maybe increasing the magnitude and not changing the direction, or maybe he can change his velocity by changing the direction. So the 2 cases are different. We are going to see the part of the vector later on. We have finished. In both cases are acceleration. So now